Good morning. The next concept is antenna apertures. Apertures are nothing but areas. So we are talking about antenna areas. There are two types of areas. One, physical area of an antenna, which is the overall structure of an antenna, and the other one is effective aperture of an antenna. Since I want to cover this topic quickly, I will not write any equations, but I will define from my notes that an antenna aperture is defined as an area through which the antenna radiates its maximum energy in the free space. So let's consider this diagram here of a simple horn antenna, and you can see this is the mouth of a horn. So physical area of this antenna is this mouth of the antenna through which the radiation is taking place. You can see here this is the direction of propagation of plane wave. Since the arrow is shown in this direction, this antenna is actually receiving it, and it is always convenient to define the apertures while we consider the receiving case of an antenna. So let's say this horn antenna is immersed in free space and it is receiving the power density S from a physical aperture AP. So if we consider the equation for the power received from the entire physical aperture, it is given by P is equal to, power is defined as the square of field divided by the impedance Z, and this power is being received through the physical aperture AP. So this term becomes S, which is nothing but a pointing vector, and AP becomes the physical aperture. The term S into AP is defined in terms of watt because it's a power term. Thus, for the horn antenna we have considered, the entire power is currently being received from the mouth, so that is its effective aperture. Next, we'll define the ratio of effective aperture and physical aperture as aperture efficiency. So it's always effective aperture which is lesser than the physical aperture. So this dimensionless quantity represents the aperture efficiency. Now in the last topic, the directivity that we have derived can be related with the aperture of an antenna. For that, we need to consider another diagram in which the same horn antenna shown in the previous diagram is receiving the energy, or we can say this in the transmitting case is transmitting the energy from effective aperture AE, and the radiation pattern is of shape cone whose beam area is omega A. At a distance r away from the antenna, the field is ER, and near the antenna the field is represented as EA. Now the power radiated by the antenna is given by the square of the field again divided by the impedance, which is the intrinsic impedance of the free space. Its value is 377 ohms, multiplied by the aperture, effective aperture of the antenna. Now when the antenna radiates this power at a distance r away from the antenna in the far field zone, the received power or the power available at this point can be defined as again the square of the field divided by characteristic impedance Z0, intrinsic impedance Z0, multiplied by the distance, square of the distance it travels R0 into the area, beam area omega A. If we compare these two equations, equation number 1 and equation number 2, and note that the radiated field ER is equal to the field from an antenna EA divided by R lambda into the effective aperture of the antenna. If we substitute this value by comparing or equating the previous two equations, we get, so let me solve this. The first equation is EA square by Z0 into AE, and the second equation is ER square by Z0 R square omega A. Let's substitute in place of ER this value. So we get EA square by Z0 AE is equal to, in place of ER we do this whole term substitution, EA square AE square divided by R square lambda square into this term as it is R square omega A. So now R square cancels, AE cancels, EA square and EA square, and sorry, this Z0 and Z0 cancels. So what remains from this equation is the term AE is equal to this lambda square divided by omega A, which can be written as lambda square is equal to omega A into AE. So this is actually an equation for lambda square, which is called as aperture beam area, because it is product of aperture and beam area. Now we know the definition of directivity from previous lecture, as it is ratio of two beam areas subtended by sphere divided by omega A, beam area subtended by practical antenna. If we do substitution of omega A from this equation here, we get directivity as 4 pi AE divided by lambda square. And this equation of directivity is, if you remember from previous video, two definitions of directivity we have already studied. So this is third definition of directivity in terms of effective aperture. So this equation makes it clear that all antennas have effective aperture, and if effective aperture varies, the directivity also varies. So we can compute directivity of different antennas from effective aperture given, or effective aperture can be computed if the directivity value is given. In the next video, we will discuss antenna bandwidth. Thank you.